Open Claude up and look inside, and you won't find rules or sentences or anything a person wrote. You'll find billions of numbers. Nobody typed them in. Training grew them. And for years, not even the people who built these models could tell you what a single one of those numbers actually meant. In this series, we've been inside Claude's architecture, its memory, how it's trained, and the safety built around it. Today, we go somewhere stranger. Interpretability. The science of reading the model's mind. The effort to look inside Claude and understand the actual mechanisms behind what it says. We'll cover why a neural network is a black box, the hidden features researchers learn to pull out of the noise, the circuits that show Claude reasoning, what happens when you reach in and edit a thought, and why any of this matters for trusting the thing. Start with the problem, because it's deeper than most people realize. When you train a neural network, you don't program it. You grow it. You set up billions of numbers, the weights, and you nudge them over and over until the model gets good at predicting text. What you end up with works. But nobody designed the internals, so nobody can just open them up and read them. The obvious move is to look at individual neurons and ask what each one does. That fails almost immediately. A single neuron will light up for the Golden Gate Bridge, and also for a particular brand of car, and also for a feeling of nostalgia, and 3 other unrelated things. It's not specialized. The technical name for this is polysemantic, one neuron, many meanings. And it happens for a reason. The model has far more concepts to represent than it has neurons, so it packs them together, overlapping, sharing the same space. Researchers call this superposition. The network is compressing thousands of ideas into a structure that's too small to give each one its own home. That's why reading the raw network doesn't work. The thoughts are real, but they're tangled together, smeared across the neurons in a code nobody handed us a key to. So if the neuron is the wrong unit, what's the right one? The breakthrough was to stop looking at neurons and start looking for features. A feature is a single, consistent concept, the idea of the Golden Gate Bridge, the notion of a genetic sequence, the pattern of a function that's about to return a value. The insight is that these features are real and recoverable, even though they're hidden inside the superposition. Anthropic uses a technique called a sparse autoencoder. Think of it as a tool that takes the tangled activity of the network and untwists it, separating the overlapping signals back into a long list of distinct, clean concepts. When they ran this at scale on a production model, they pulled out millions of features, and they were interpretable. There's a feature that fires for the Golden Gate Bridge whether you mention it in English, in Japanese, or show a picture of it. There are features for code bugs, for gender bias, for flattery. Most strikingly, there are features for abstract and even dangerous ideas, a feature that activates around deception, one around the concept of a hidden agenda. For the first time, the smear of numbers had a legend. We could point at a specific pattern inside Claude and say that right there is the model thinking about this exact thing. Features tell you what Claude is thinking about. The next question is how those thoughts connect into reasoning, and that's where it gets remarkable. Features don't fire in isolation. They feed into each other, in chains, and those chains are called circuits. By tracing which features trigger which, researchers can watch the model reason step by step. Ask Claude for a rhyming couplet, and you can see it activate the rhyme target before it writes the line that leads up to it. It's planning the ending in advance, not improvising word by word. Ask it a simple math problem, and you find it isn't doing the arithmetic the way you were taught. It's running several approximate paths in parallel and combining them. Ask the same factual question in different languages, and the same core concepts light up in a shared internal space before the answer gets translated out into words, evidence of something like a language of thought underneath the language on the surface. This is the part that changes how you think about the model. It isn't only predicting the next token in a fog. Inside, there are structured, multi-step computations, mechanisms you can actually follow. The black box isn't fully open, but we've started reading the wiring. Here's how you prove you've truly found a thought and not just a coincidence. You reach in and change it. If a feature really represents a concept, then turning it up or down should bend the model's behavior in a predictable way. So Anthropic tried it. They took that Golden Gate Bridge feature, clamped it wide open, and the model became obsessed. It would steer almost any conversation back to the bridge, insisting in some cases that it was the bridge. They called it Golden Gate Claude, and as a demo it was funny. As science it was profound because it proved the features are causal. They're not passive labels we painted on after the fact, they're the actual levers the model computes with. Turn the deception feature down, and you can make a model more reluctant to lie. Turn a safety-relevant feature up, and you change how it handles a risky request. Now you can't ship a model by hand-tuning millions of dials, and oversteering breaks it. But the principle is established. The internals aren't just readable, they're editable. That's a fundamentally different relationship to have with a piece of software you didn't program. One where you can open the hood and adjust a specific idea. So why pour years of research into this? Because every other safety method we have judges the model by its output, by what it says. And a capable model can say all the right things for the wrong reasons. It can be confidently wrong, or worse, deliberately misleading, and the words on the screen won't tell you which. Interpretability is the only approach that aims at the reasons themselves. If you can see a deception feature light up while the model gives you a clean-sounding answer, you've caught something no output filter ever could. The long-term goal is an honest-to-goodness audit, the ability to inspect a model before you trust it with something serious and ask mechanistically, what is it actually doing in here? We are nowhere near finished. Today's tools recover a fraction of what's inside, and a great deal stays dark. But the trajectory is the point. For the first time, the black box is not permanently black. And for anyone building on top of Claude, that should reframe how you think about it. Not as an oracle you take on faith, but as a system that is, slowly, becoming something we can actually inspect. That's interpretability. From a smear of billions of numbers to features, circuits, and thoughts you can edit. We can finally start to read the mind we built. If this was worth your time, subscribe. Next, alignment, the question underneath all of it. Not whether we can steer Claude, but whether its goals actually match ours.